So let's take a second, and more than a second, and talk a little about the metric system, how to do measurements, and how to do some metric conversions. We play with the metric system in the lab because science uses the metric system. And even though we might be uncomfortable with it if we didn't grow up with it, once you give it a chance, you'll find that it's pretty user-friendly. The metric system is all based on units of 10. And here's what I mean. In the English standard system that we use in the US, if I talk about length of an object, I have inches, feet, and yards, right? Well, I have 12 inches equals 1 foot. 1 foot is 12 inches. If I take 3 feet or 36 inches, that equals a yard. So you can go back and forth between using feet, yards, or inches to talk about an object. The weird thing about the English standard system, though, is, who made that choice, right? It's 12 and 3 and 36. Well, the metric system is far more user-friendly and takes a common sense approach. I can talk about things like a foot and having something being bigger or smaller, like a yard or an inch. But this time in the metric system, we're going to use units of 10. So I might have one object, and if it's 100 times smaller or 10 times smaller, I call it something. If it's 100 times bigger, I call it something else. It would be as if the English standard system said this. All right, I have 1 inch. 10 inches equals 1 foot. 10 feet equals 1 yard. If the English standard system did that, it would work like the metric. So let's look at this little line here that represents some of the commonly used units of measure for the metric system. We're going to start right here. We're going to refer to these as our points of reference, our basic units of measure. And the basic unit is a gram, noted by a G. That's for the mass or weight. Then we have liter, noted by an L, which is the volume of a liquid or a space. Then we have meter, which is the length of an object, and it's always noted by M. I'll give you a couple of reference points. A gram is a little thing. A liter is about as big as 1 quart is, or 32 ounces of a liquid. A meter is a little bit bigger than 1 yard. So it gives you an idea of how big our basic units are. So again, our basic unit of measure, our reference point, is the gram, the liter, or the meter. So let's go big first. Let's say I have an object and I weighed it, and it is 1,000 grams. This is a big object. Well, I would call that a kilogram, and I would write it as a kg. Anytime you use a kilo, that is 1,000 times bigger. So I can have a kilogram, a kiloliter, or a kilometer, or kilometer. So again, a kilo is big. It's 1,000 times bigger. So there's 1,000 grams for 1 kilogram, 1,000 liters for 1 kiloliter, and 1,000 meters in 1 kilometer. The beauty of the metric system, in addition to just dealing with zeros, is that the rules are exactly the same. So a kilo is always 1,000 times bigger, and it doesn't matter if it's length or volume or weight. The rules are always exactly the same. So in biology, that's the one we use that's bigger. If you took chem, I know there's a bunch in between, but in biology we're going to stick with kilo as being the one that's bigger. And in biology we have these 3 here that are smaller that you need to be responsible for. If I take a gram and I chop it up into 100 equal units, each of those units would be a centi. So I'd have a centigram, I could have centiliters, or centimeters. So again, a centi is 100 times smaller than our unit of measure. So it takes 100 centigrams to equal 1 gram. 100 centiliters to equal 1 liter. 100 centimeters to equal 1 meter. The next level down, or smaller, is called a milli. So I have a milligram, a milliliter, a millimeter. A milli is 1,000 times smaller, so 1,000 milligrams in 1 gram. 1,000 milliliters in 1 liter. 1,000 millimeters in 1 meter. Now we can go even smaller. We can make something 1,000,000 times smaller. And that is called the micro, which in text, like typewriter text, is usually a little U-shaped text there. So a microgram, a microliter, or a micrometer. So there's 1,000,000 micrograms for 1 gram, 1,000,000 microliters for 1 liter, 1,000,000 micrometers to 1 meter. Now they're not here and you're not even responsible for them in the lab, but realize in the world of physiology, we also have picos and nanos. A nano is a billionth. It is 9 zeros. A pico is a trillionth. It is 12 zeros. And when it comes to those hormones in our bodies for homeostasis, sometimes our bodies communicate in terms of nano and picograms of hormones. But we're going to focus on these. So you may want to pause the slide and go through each of these units of measure and answer the following questions. Which of these is bigger or biggest? And if so, how big is it? Which of these are smaller? And if so, how small are they? Now when we use metric system to do metric conversions, we're going to say things like an object is 1 liter. How many milliliters is that? That's what we mean by metric conversion. The object itself hasn't changed its volume. I'm just changing how I talk about its volume. There are several methods to accomplish this, and we'll get to 2 of them. If you know an alternate method, you're certainly invited to use it. For simplicity's sake, we're just going to talk about a couple of them. One of them uses conversion factors. I'll show you that. And another just uses the fact that if you divide and multiply units of 10, aren't you really just moving decimals around? And when we get to the decimal, we're going to use these numbers up here. So here's what I want you to think about for now. If I take a gram and I multiply by 1,000, there are 3 zeros there. That's 3 decimal spaces. If I take a gram and I chop it into 100 units, there are 2 zeros there. That represents 2 decimal spaces. To go from a gram to a milli is going to be 3 decimal spaces because there's 1,000. And what do you think? To go from a gram all the way to a micro, to go from 1 to a million, how many zeros are there? 6. So we're going to come back to this concept of how many decimal spaces are between each later. Let's look at how we measure. If you want to measure length, you're going to need a metric ruler. And quite often rulers come with English and metric sides. So you have to know what's the metric side. This side right here is the metric side. Each number represents 1 centimeter on this ruler. Each individual little line, see all these teeny little lines? Each individual one is 1 millimeter. So you can see this ruler is about 35 units long. Okay? Or 30.5 centimeters. The other side, where you see big fat designations and the numbers are far apart, that's always the English side. An inch is big. There's about 2.5 centimeters that equal 1 inch. So a centimeter is quite a bit smaller than an inch is. So step number 1, if you're measuring the length of an object, number 1, check to see that you're on the metric side. The second thing you're going to do, erase here, when you go to measure the length of an object, is line your object up with the 0 line. Line the other end of your object up to, wherever it ends. So you're measuring this object from its start at the 0 line, not the end of the ruler, the 0 line, to where it ends. And now just count. We have 1, 2, 3, 4, 5, 6, 7, 8, not quite 9. 8.1, 8.2, 8.3, 8.4, 8.5, 8.6, 8.7, 8.8 centimeters. That's what this object, this line that I drew here, that's how long it is, 8.8 centimeters. By the way, putting the unit is just as important as the number. If I walked down the street and I walked up to you and I said, hey, 7, you'd probably go 7 what? Okay? So you always have to have the unit as well as the number. So that's how you do length. Get your metric ruler, determine which side is the metric side, line one end of your object up with the 0, not the end of the ruler, but the 0, and count the number of centimeters or millimeters up till your object ends. If we want to do volume of a liquid, we have a couple of options. There are going to be 3 things in the lab. One's a beaker, one's a graduated cylinder like this, the other is a pipette. A beaker is really just a glass jar meant to carry things around a lab in. It's not at all accurate. But a graduated cylinder is pretty accurate. A pipette is most accurate. So when we measure the volume of a liquid, we're going to use graduated cylinders or pipettes. Now, the bottom of this graduated cylinder is way down here and it starts at 0. And it's at least gone up to 50. This right line here represents 50 milliliters. Here's the 60 milliliter line, and who knows where it ends, way up there. If you look here, we can see where the water line is. Water's kind of funny. Water molecules are sticky and they tend to stick to the side of the glass. So if we follow the actual line, it's high, then it comes down, and it goes back up again. By convention, we always measure this lowest spot right here. That's called the meniscus. So we're going to measure liquids at their meniscus, at their lowest spot. At this point, it becomes kind of like using a ruler. Start at the 0, count your way up by 10s. That was my 40. So if we get up to here, we have 50 milliliters. And now you can see it's somewhat above 50 milliliters, but definitely less than 60. So your next step then is to look at the graduations on the cylinder. Not all graduated cylinders are created equal. This graduated cylinder happens to go 50, 51, 52, 53, 54, 55. Oops, 56, 57, 58, 59, 60. This graduated cylinder happens to be in 1 milliliter increments. Not all of them do that. So when you measure with the cylinder, always double check. Some of them will use 1 line for every 2 milliliters. So you have to just count them out. But again, once you get liquid in there, once you find the meniscus, you're really measuring the height of this column of water from the 0 all the way up to the meniscus. So here it goes 50, 51 mils, 52 milliliters. Here's the 53. It's not quite 53. So you could call this either 52.5 milliliters. If you said 53 milliliters, I would take it. If you said 52 milliliters, I'd accept it. If you said anything else, you're too far off and I wouldn't accept it. So we would say that this liquid's volume is 52.5 about milliliters. A pipette is the same concept. You measure from its tip at the 0 to the meniscus, and you really just count lines. You can use your whole numbers. The deal with a pipette, because they're used to pull liquid up and release liquid, they tend to have two scales on them. So you always want to use the scale that has the 0 at the tip of the pipette. But otherwise, you're measuring the height of this column of liquid from the 0 line to its meniscus. So that's volume. But what if you want the mass or the weight of an object? In our labs, we use a triple beam balance that looks like this. Okay, you put an object in this pan, and you use these sliders here to try and get this arm to be on a 0 line. There's an order in which you use the sliders. So if you were measuring an object, always put all the sliders on 0 in their initial position. Put the object in the pan. Use your hundreds first. This is going to be, you're going to have hundreds, tens, and ones. Use the 100 slider. Go from 0 to 100. Put it in the 100 slot. See if this thing drops. If, say, you put the slider on 100 and this arm doesn't drop down, you're still too light. You have to go another 100. But move the hundreds one slot at a time until this arm drops down. Then go backwards 1. At that point, leave the 100 in position. Do the same thing with the 10 slider. Go one slot at a time until you find the point where you're too heavy and go back 1. Lastly, use the ones slot. Do the exact same thing. So it's always the hundreds, then the tens, then the ones. I'm not going to play it in the interest of time, but copy and paste this URL into YouTube. It's a great step-by-step animation on how to use a triple beam balance. It doesn't have sound, so I recommend watching it a few times and talking it out loud to yourself, but it's a great video. When you're done with that one, go back into YouTube and just put in how to use a triple beam balance, and you'll get several other videos that show you how to do it. And then, as always, you're going to practice in lab. Alright, so let's pretend we actually measured some objects here. And we have some data, which is what you do in the lab. You measure the length of a finger, or you measure the volume of a liquid, and then you do conversions on it. So let's pretend we measured an object, and it came out to be 5 meters in length. And I ask you to tell me what that is in terms of millimeters. So this, again, is a conversion. Now, there are more than one way to do a metric conversion. There are many, many methods out there. I'm going to show you 2. Choose whatever method works best for you and practice it a lot. The trick is to trust your data and trust your numbers. Sometimes with the metric system, you will get decimals. And if you're not used to it, people tend to freak out, think they did something wrong, and start changing answers. So just double check that you set your math up correctly, and don't change or freak out if you see decimals. Alright, method number 1 uses conversion factors. Okay. Method number 1 says, alright, step 1, trust me on this, draw a big plus sign. Step number 2, ignore the numbers for now. Let's just set up our units first. So in this box right here, write in only the unit I was given, which is meters. Step number 3, write meters again down here on the exact opposite diagonal. Step number 4, above it, write the unit I want to end up at. Step number 5 is now add the numbers. What happens is people want to jump straight to the numbers, and if you're not used to doing that, invariably you set the conversion up incorrectly, and then the answer ends up being wrong. So if you're not comfortable with these conversions, use this kind of 5-step method just to set up the units first. Then plug in what you know. And if you look at just the units, what have I done? I've set it up so that meters cancel out. So instead of trying to memorize this over that or that over that, or 1 over x equals 12 over 3, if you're not used to doing any of those ratio methods, try this method of just setting up the units. So at this point, let me see if I could change colors. If I add in what I know I have 5 meters. And now over here you have to add in, well, what's the relationship between the two? Well, for every 1 meter, I have 1,000 millimeters. Now let's just do the math. This is my dividing line. So this tells me 5 times 1,000 over 1. 5 times 1,000 over 1 is 5,000 millimeters. Don't forget the units. So that's one method. So what I'd recommend is you pause the slide. You can go down here and click that pause button. Okay. Pause the slide and practice this conversion, this method, a couple of times. Then come back and we'll do the second method. Hopefully you followed my advice. The second method is based in this math. And the second method says, okay, let's just boil this down to a couple of rules. And rule number 1 says, if I go from a large unit of measure, like a kilo or a gram, over to a smaller unit of measure, like this just did, this went from meters to millimeters, what happens is my decimal is going to slide to the right because I'm going to have to multiply things. The other rule is just the exact opposite. If you go from smaller unit of measure to a larger unit of measure, your decimal really is going to slide to the left because you end up dividing things. So that's the first set. What direction are you moving on that line we had a few slides back, This line. Are you moving this way or are you moving that way? Okay. The other is how many decimal spaces are you going to slide to the right or to the left? And the number of spaces is based on the numbers of zeros. So here in this example, I'm going from meter to millimeter. Is that small to large or large to small? That's a larger to a smaller, and my decimal is sliding the same way as my finger would move on that little metric line I gave you. So my decimal is going to go to the right. The hardest part is figuring out how many spaces. And it's the difference in the numbers of zeros. There's no 0 here, but there's 1,000 here. There's 3 zeros here. So this is actually going to slide 3 spaces to the right. So it starts here, and we're going to go 1, 2, 3. Give it a new home. Fill in with zeros. Okay. Now rewrite it so it's neat. 5,000 millimeters. We're going to do a couple more conversions, and we're going to do them with both methods so you can get the hang of this. Choose one or choose any of the others out there in the world. Practice it till you're good with it and stick with it. Next example, object is 72 centimeters. What is that expressed in terms of kilometers? So let's do this method first. We may have to do a couple of steps. So I do my sign, and I go centimeters, and then I write centimeters here. This point you got a choice. You can either jump from centimeters to kilometers or work your way up. I like to work my way up. So I would go from centimeters to meters, meters to kilometers. So what's going to happen? They're going to cancel out. They'll end up canceling out. So I just set it up by units first. Now, let's plug in what we know. We had 72 centimeters. For every 1 meter I have, there's 100 centimeters involved in that. And for every 1 kilometer I have, I actually have to have 1,000 meters. If you're wondering where I got those numbers, that was way at the beginning of that line when I was saying there's 100 centimeters in 1 meter. or 1,000 meters in 1 kilometer. Now we've set ourselves up here to go 72 times 1 times 1 over 100 times 1,000. Okay? So you could run the math. The other method said, well, 72 centimeters to kilometer. I'm going from small to a large, which means my decimal has to go to the left. And the hardest part now is I have to figure out how many. It takes 2 zeros to get from centimeter to meter. It takes 3 more zeros to go from meter to kilometer. That's a total of 5 zeros. So you're going to go 5 spaces to the left. The decimal starts here, so we're going to go 1, 2, 3, 4, 5. Give it a new home. Plug these spaces in with zeros. Rewrite it so it's neat. So this is now 0.00072 kilometers. This is the point where someone on a lab exam panics because they're not used to seeing zeros. If this happens, and it will with the metric system, just double check that you set it up correctly. And if you set it up correctly, leave it alone. Key number 2, always, always, always include the 0 to the left of a decimal. And here's why. Let's pretend you're a pharmacist. And you work with the ER doctors. And you're not in a clinic today that has a computerized system. So the doctor writes you a script. Quick, 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 someone's dying. Okay, which of these is 5 and which of these is a half? Quick, someone's dying. Too late, they died. Okay. The point is, leaving something as a whole number is obvious. Putting a point and a number isn't always obvious. This happens all the time. Patients are often overdosed by a factor of 10. So protect yourself and your future patients by putting a fat 0 and the 0 to the left of that decimal, a nice big fat 0 there. There is no arguing that that is 0.5 or a half. But you can argue that because, you know, that could be a fly speck, piece of dust. We don't know what the heck that is. All right. Here's another one. An object weighs 37 kilograms. So we're dealing with weight and mass now. What's that expressed in terms of centigrams? And guess what? The beauty of the metric system is it doesn't matter. The rules are exactly the same. Now my brain really does like this method. If I go from kilogram to centigram, am I going from larger to a smaller or smaller to a larger? You're going from something that's kind of big to something that's smaller, so my decimal's moving to the right. Now let's figure out how many spaces. Well, it takes, from kilo to meter, it takes 3. And to get from meter to centi, it takes another 2. Ah, it's a total of 5 again. So this time we're going 5 to the right. The decimal started right here. So we go 1, 2, 3, 4, 5. Give it a new home. Fill it in with the zeros. Now let's rewrite this so it's neat. 3, 7, 0, 0, 0, 0, 0 centigrams. Again, people panic because that's a lot of zeros and that number looks weird. But if you just check that you set your system up correctly, trust the numbers at that point. Okay. By the way, you may have noticed a trend. When the unit gets smaller, the number gets bigger because it takes more of them. So it takes more millimeters to equal the meter, right? So that's why 5 meters is the same as 5,000 millimeters. Millimeters got smaller, but my number got bigger. Last one, volume of a liquid, 17.3 milliliters. But even though this is a volume of a liquid and not weight or not length, it does not matter. The rules are exactly the same. So pause this slide, choose a method, work out this number. Tell me in class what you think the answer is. So here's some things to keep in mind. if you're asked to do a metric to metric conversion, you do the methods we've been talking about, and you have options. But if you go English to metric, inches to centimeters, pounds to kilograms, you cannot slide a decimal because the units aren't related to each other at all. You have to use conversion factors. So I recommend you use that method of setting units up first. Now, on the lab exam, if it's an English to metric system, a calculator will be there. The units will be there, the factor, but you have to know how to set it up. So let's pretend an object is 41 inches, and you get told there's 2.54 centimeters for 1 inch. Okay, how are we going to do this? Well, we're forced to do this, baby. So we make our plus sign, we write in the unit in this corner, write it in again in this corner, so we force it to cancel out. Go up above, write the units you want to end up at. Now, plug in what you know. We started with 41 inches, and for every 1 inch, it is 2.54 centimeters. So now we've set up a math problem where we have 41 times 2.54 is 104.14 centimeters. Why 2 decimal spaces there? Well, because there's 2 here. So you usually match the number of decimal spaces to the information that you're given. Alright, so things to remember for this metric system exam. If it's a metric to metric conversion, you have to be able to do it on paper without reminders, without conversion factors, without notes, without calculators. You have to practice and show your work. If I just get an answer, I don't know where you got that answer from, so I need to see your work. If it's an English to metric conversion, a conversion factor like 2.5 centimeters to 1 inch or 2.2 pounds to the kilogram, the conversion factor and a calculator will be provided. But you still have to know how to show your work and how to use that conversion factor, how to set up the problem. Also make sure for the metric and measuring, you know how to use that triple beam and that pan balance accurately and quickly. Start with the hundreds, then the tens, then the ones. Okay, practice that. Also know how to read milliliters of a liquid in a graduated cylinder and in a pipette. Practice that. Know what the most accurate method of measuring volume of a liquid is. Is it a cylinder, a beaker, a pipette, and why? Make sure you go through all the questions of the lab manual for this and double check that you have the correct answer. And that is it for metric system and measuring and reviewing it. You can also pull up a lot of Google images of the pan balances and pipettes and things and use that to practice as well.